Swiftly on now, my colleague Andrew Kingdon from EGS in Keyworth. Andrew is a petrophysicist and a team leader of parameterisation and statistics. The world has become so much more complicated when I first joined EGS. You're going to tell us about the stochastic modelling work that your team has been doing in the
This is, hi, Andy Kingdon. This is a summary of a lot of work by a lot of people. But before I talk about the how and the what, I'm going to talk about the why. BGS exists to answer questions, and always has. And we sit in a space between three essential groups of stakeholders. The UK government at all levels, from local to national to UK-wide. Academic researchers, UK industry. And we can exist at any point in that space. But always, we're really working towards a third dimension of the tetrahedron, which I couldn't actually find a way of drawing in PowerPoint, with the UK public sitting above us. And in that space, we answer questions that meet those requirements. But we're also moving from a world where we just say, this is what is, by describing the geology, to answering what if, scenario planning and decision support. So some questions that you might need answered about a city include, what are the impacts of hidden ground conditions? What are the impacts of subsurface properties on surface drainage? What are the impacts of the subsurface on containing or reactivating anthropogenic contaminants? What are the impacts of subsurface risks on essential urban infrastructure? And until now, we've basically drawn lithostrophic maps that define generalized geology, and then 3D models that define a geological structure in which those units sit in. But they don't adequately tell you the answer to any of the questions above, because geology is heterogeneous on very many scales, and you need to get a value on that heterogeneity to actually to be able to say, what does this mean for my project? So what we're looking at is new techniques that are needed to understand subsurface variability. Unfortunately, the oil industry has done all the work for us with this. So what we're trying to do is apply oil industry reservoir modelling to understanding the sediments of a city. And 80% of our population is now urban, and that's the density of those people is increasing because we're trying to minimise the sprawl of our cities. So Glasgow has been the perfect test case for all of the above. It's a large post-industrial metropolis. Redevelopment is needed now, it's needed for jobs, it's needed for housing, and there's a legacy of contaminated industrial sites needing remediation. And I think it's really important to say that Glasgow City Council has been an exemplar of a stakeholder. They've got some advantages. They govern most of the city in a way that most local authorities don't in other UK cities, which is divided up between several councils. But they're directly involved in development via Clyde Gateway and other projects. And by insisting on the deposit of site investigation data with BGS, they've built a unique database of subsurface properties. Therefore, we have a unique standardised data set sufficient to actually try something new in Glasgow. So here is a map of the central Glasgow area that we're talking about for this work. And typically, we would have in the past attempted to answer questions using either bedrock geology maps of the sort that Alison has been talking about extending to the third dimension, or superficial geology of the sort that Katie is talking about extending into the third dimension. But the real problem is this, and Katie's alluded to this already. We have a glacial package of sediments, amongst others. We have many sediments in the city, but they're hugely heterogeneous. This slide provided to me by Tim Kearsey just shows the variability of materials that we have to deal with. This is a section of the Guruk sand member and the Clyde Bank clay formation. It's hugely heterogeneous. How do you understand how that affects your project? So we're going to use stochastic modelling. As I say, this comes from the oil industry because standard geological map basically works deals with the world in this form. You find the top and the bottom of a unit and you give it a name, and that name describes something about its properties and its history and so on. But fundamentally, the only description of its variability is whatever you use in that name. Now, a stochastic model can just be a random function applied to that to say it varies around a set of normative properties. But where you have boreholes sampling it, you can actually use it to build a robust statistical assessment of how much it varies and where. And you can run multiple realizations of that to try and understand that. So this is the outputs of our lithology model of the superficial geology of Glasgow. And that's the plan view and two cross-sections showing some of the fascies that you can get from looking at the most frequently occurring lithology in that package after 500 simulations. So there's some robust statistics. You've taken our input data and extrapolated that through a 3D space. So what we wanted to do is build on that, use that framework, as a way of populating physical properties into that space. So this is the map of the physical properties we have measured in Glasgow from site investigations in the superficial geology package. And as you can see, they're clustered in certain places, the M74 motorway extension and some of the main redevelopment sites. So we've not got a completely consistent package of input data, which is one of the problems, but nonetheless, we've been able to do that by able to use that to make a stochastic property model between the base of the made ground, the top of the real geology, and the top of the rock head, the top of the solid geology. So, and into that space we put data from technical data, and we started with density because it's a nice, simply understood physical property, and calculated summary statistics from it. So that is a map, 3D view of the top base artificial ground, and boreholes hang below that space, which have physical property measurements against them. And then underneath that is another surface, which is the rock head, and we filled that envelope with properties by building a grid through it. So we start off by taking our lithology data and attributing it with physical properties from direct measurements. And then we do a calculation of density residual. I'm not going to test you on this afterwards, but basically we take the value and we each point and subtract the lithology mean. We calculate a variogram, and then we do a sequential Gaussian simulation. I hope you're taking some notes here, where we do 500 separate simulations of this to try and get an assessment of how much these individual packages vary. And then we recompute an actual value and then attempt to visualize it. So we do a bunch of summary statistics. So we've got a series of lithoclasses which over a period of time we know are representative of the geology. We've been through this cycle several times to try and improve this and make sure that we're dealing with repeatable units of geology. So we've calculated summary statistics for a whole set of these different packages and calculated from each of them the number of occurrences and mean, median, standard deviation. And we can put that into a variogram analysis. I'm not going to try and explain the detail of that, but all geostatistics works on the principle that as you get further away from somewhere, the relationship between the 2 points decreases until some critical point is crossed where there is no relationship between that. So these are well understood physical property, statistical techniques for looking at variability. Right, so this is actually what we're talking about. This is the 10 by 10 central Glasgow square. All of these models are showing plan. It's just easier to show the detail in plan view. But that is one simulation of how a bulk density across that surface. Each of these is actually in 3 dimensions. So there's 3 planes in the model I've just shown you there, X and Y, and a tabular surface, flat surface, through part of that succession across the Clyde River Valley in this case. So each of these models is the same. So we've done, this is another random simulation. This is the third. They're all done by different statistics. Depending on where you start your model, you'll get a different output. But if you do this enough times, and we're doing this typically to 500, which is about what we can compute in a sensible amount of time, you can then build a model that has a sensible realization of the variability of that space, because you can produce a mean. So these are the summary of the mean values in each of those grid squares after 500 simulations. And what you're seeing here is that, perhaps not surprisingly, the glacial materials on the north and the east of the city are higher density than the fluvial package in the, through the city centre, through the Clyde River Valley, and you're seeing a very low density materials here, right where you would probably be wanting to develop these sites further. So these are indicative of potentially problematic ground conditions for putting large buildings on top of it, just where you might want to do just that. And we can also, this is a map of the variability. Interestingly, here you can see very clearly the line of the M74 motorway through that track there. That's because you have a very high resolution data set at that point, derived from the site investigation for that motorway. So we got a much smaller margin of error in this. Now, it has to be said up here, there's very little data, so we cannot make reliable predictions of likely ground properties there. Anyway, so we've created a procedure to create a property model of a citywide space, conducted a number of resolutions of it, and then we can study 3D properties at any point in that sectioning along particular lines. So we can look at the likelihood of poor ground conditions. This can be improved iteratively, new data becomes available. If somebody starts development on a new site, you can pull that new data in, recompute that in a few minutes to hours, and make that data almost immediately available so that people can use it as they progress a site investigation to improve the model that they're working on. It's been done multiple times. We're happy that we now have a robust workflow for dealing with a physical property like bulk density, and that workflow is now well understood by those of us working on it. So if people ask us to repeat this, we can do at a different scale, for example. Now, we've been testing this model in the last few days. We've taken 10% of the input data out, not included it in our bulk density interpretation, and then compared it with the known values which were not included with the interpreted values in the grid. And this graph here is a representation of that. Now, clearly there are some outliers, perhaps here, but we seem to be getting a good relationship between our expected values and our actual measured values. So we believe we are showing robustly information that is useful to people on how to plan for poor ground conditions. A second physical property we've done, I'm not going to talk in any length about this, how we did this, but Andrew McDonald is in the room. He's created a new model of hydraulic conductivity derived from particle size distribution. So he's taken geotechnical particle size distribution information, calculated a proxy of hydraulic conductivity from that, and tested that statistically, and we are happy it represents a good model of this. And then we've again simulated it in the grid in the same way. It's slightly more complex with something like hydraulic conductivity because you have to log the data because it's a logarithmic function. But again, we've run it through the same workflow and built a series of stacked simulations of hydraulic conductivity in that space. So we can look at the likelihood of water to flow into the ground at any location over a time interval. So in this case, we've presented it as a probability map of the likelihood of very low hydraulic conductivity on a scale where red is there is low conductivity and blue is much higher conductivity. So as you can see, again, perhaps not surprisingly, up here in the northwest, where typically diamectite porous glacial clays, you're acting as a good seal on the ground, so you're not getting a lot of runoff, whereas here down through the Clyde River Valley, you're seeing there are zones of very high conductivity. Now, if you've got an industrial site on that space with post-industrial contaminants in that site, there therefore is a danger that higher inflow might cause those to be reactivated. So it gives you a grounding of a serious problem. And to make clear, this is a three-dimensional model. I'm generally only showing the plan because it's just easy to get your head around. But we can actually look at the potential pathways for contaminants to be moved away. So give you an indication of the risk of a function of those becoming reactivated. What we're now trying to do is to take this data and supply it to groundwater modelers to produce a better, more detailed groundwater model based on real understanding of the physical properties. It's a difficult problem because it's difficult to get the computing power to compute it. We've hit the limits of what we can easily compute, and we're working on this now. So again, we've created mean and variability via standard deviation, so we can genuinely understand not just what is one possible outcome for this, but deal with the consequences of lots of different input data simulations, so that we can understand the likely variability of the response at any point in our grid. So what does all of this mean? Well, we built two workflows that allow us to look at how things vary in 3D space. One marked here in blue. This is very much simplified, but basically a system for developing lithology models that allow you to look at the variation of lithomaterials, and then from that, one marked in red, which looks at the variation of physical properties in 3D space. So we can build stochastic property models which should enable us to provide solutions to solve societally relevant problems. We've developed a workflow to create robust stochastic models on a citywide scale, and we identified some limitations of this approach, and basically they're about the availability of good data and the quality control of those input data sets. And we spent a lot of time working back through our lithology data sets, making sure that our litho classes are actually representative of the material and making sure that we know what was there and therefore what its effect will be. So we've learned some stuff, and this is really quite important. Data standards resolve both of those issues I've just highlighted, and providing the input data in a form that can be then reused with the minimum amount of recomputation is really important to this. Glasgow is an exemplar of how to do that, and Glasgow as an area is very lucky that people have had the forethought to think about these things. And let's big ourselves up. The BGS CUSP project has shown vision in developing this kind of work for the benefit of a city. These databases, if spread out to other places, will allow development and management of this, and therefore management of things like contaminant issues in other UK cities. But it can't be done at the moment. Glasgow is the exemplar of understanding urban geology because it has created a framework where that data can be deposited. And as of yet, work of this level of detail cannot be replicated in other UK cities, and by extension in most cities in the world. So, with the exception of our Dutch colleagues, Glasgow is better understood, or can be better understood on a level than more or less any other place on Earth, which is quite staggering. Just some wider conclusions. Parameterised physical property analysis in 3D will allow us to understand subsurface conditions citywide, aid developers in avoiding unforeseen ground condition issues, and help in decision making and planning development. It could be used to look at reactivation of contaminants, for example. It directly improves understanding of development potential of urban land and could be used as part of the pre-planning of the site investigation process. It provides information not available from more traditional geological techniques and allows development of iterative models which can be easily updated as new information becomes available. And I'll be very willing to talk to people from the geotechnical industry and the City Council about how we can actually help you move your work forward using these kind of techniques, because I think we have a conversation to have. Many thanks. Yeah.
I mean, I assume you get in contact with SEPA and so on, but is there any chance of getting a commitment to furthering this sort of development in the Clyde subbasin management plan, actually written up, so that all the stakeholders in that process, local authorities, the Environment Protection Agency, and Scottish Water and so on, could then actually have a commitment to it?
I think we're one stage away from that at the minute. The models that Majd is going to show this afternoon use a simpler understanding of the geology, and we need to increase our ability to compute the density of the grids in order to put this level of complexity into a model, and just genuinely make sure that we can compute it in a sensible amount of time we can answer those questions. But when we've done that, and we're investing in our computer hardware and our computer software in BGS to allow us to do this, this is very much work in hand right now, then I think the conversation you just said is something we really need to do, and I should be looking at Dermot to help me make those contacts. And because, yeah, the whole aim of this should be we're trying to tell you more about the problems that you have and help you define scenarios that need testing, and a group of stakeholders like the one you just described have to be involved in that process.
Direct experience of relevance of these issues, of the issues that this sort of modelling would address, was the short field primary issue, and detecting river fires and all that sort of stuff from the leachates and migrations. And there was an awful lot of discussion between Scottish Water, Scottish Environment Protection Agency, the local authorities and consultants, and trying to establish some sort of framework which is acceptable to each party to reach a common understanding of the problems.
We tried to get access to the detailed lithology model from the Shorefield site in order to do that kind of thing. Unfortunately, we haven't got access to those data yet, but it'd be very interesting to work back over that now. Hopefully that will become available to us soon. And then when it is, we can then say, okay, this is what we could have told you if you'd have provided it to us closer to the time. There's not a criticism, it's just simply getting access to a controversial site like that is always going to be complex, but hopefully we can do that in the future, yeah.
I think we'll probably have to move on, but I think I should point out that Simon Watson there, formerly of Glasgow City Council, was absolutely integral in making this project happen. And that
Thank you.
that you referred to just now.
Thank you.
Thank you very much.